Good morning, sir. Am I audible, sir? Good morning, sir. Sir, Miss Fatima is joining within 2 minutes, so we will start after 2 minutes, sir. Now,
fine.
Making you the presenter, so you can share, sir, your screen and presentation.
Okay.
So first, good morning all. So our today's speaker, Professor Uma Mahesh sir. Professor Uma Mahesh sir is HAG professor in Department of Civil Engineering, NIT Warangal. He has done his BTech in Civil Engineering from Osmania University, Hyderabad in year 1984, Masters in Water Resources Engineering from IIT Kharagpur in 1986, and PhD from NIT Warangal in 1995. His research interests and activities are in reservoir operation and management, hydrological analysis, modeling, irrigation management, watershed management, water resources system, water quality modeling and management, remote sensing and GIS application, neuro-fuzzy applications in water resources. He has more than 30 years teaching and research experience. Professor Uma Maheswar authored more than 60 peer-reviewed journal papers and book chapters and presented 50 plus papers in national and international conferences. He has handled several research and consultancy projects like Warangal Watershed Development Project, Integrated Urban Flood Management in India, Technology-Driven Solution, Real-Time Flood Forecasting using SWOT Model, Integrated Water Management Model for BIS countries under climate change scenario, and many more. Professor Uma Maheswar has also guided 11 PhD students and more than 100 master students. And at the present time, he is guiding 7 PhD and 4 master's students. Now, I request to Professor Uma Maheswar, please start your lecture, sir.
Thank you, Dr. Manish, for your nice introduction. So good morning, everyone, and welcome to the second day of the three-day training program. So let me just give me a minute. I'll share my screen and start my presentation. So is my screen visible?
Yes, sir.
Okay. So I'll be speaking on flood hazard risk assessment as my today's lecture. Obviously, it's a kind of a wide topic, and then I'll not be able to discuss elaborately all the methods and methodologies available, tools available for flood hazard risk assessment. So I'll be just giving an overview of how we assess this hazard and risk, and maybe I'll just talk about. I'll start with a kind of definition of what is flood hazard and what is flood risk, and things, and then what is the way in which you actually assess the flood risk, and maybe an overview of different methods that we use for flood risk. And I will present a case study. The case study that present is what actually we have done for an urban area. So though in fact we are talking about riverine floods here, but I think whatever we did for urban floods, I think that be applicable for even riverine flood or fluvial floods also. So this is what I'll just try to cover in the next 1 hour of time that I have in the schedule. No, flooding is, as you all know, it's a kind of a global challenge. In fact, if you try to look at the major natural disasters and the number of like the people exposed to this natural disaster and number of deaths between over the last slightly more than 1 century, 1900 to 2016, you find drought is one of the major natural disasters which is affecting large population and in fact large deaths also. But in fact, I think the impact of drought has reduced from last 2 or 3 decades. But if you look at floods, though it is very, say, large number of people were, say, in fact, dying because of floods still 1960s, the number of deaths have decreased, but still you find that almost every year, there are at least some areas in the world where the floods, people are exposed to floods and there's some deaths that are taking place because of floods. So I think as on today, it's next, it's second largest after the earthquake and then extreme weather, say, kind of natural disasters. And in terms of the losses, economical loss, in fact, there are 15 countries which actually I think are the top 15 countries. If I just list out the economic loss in terms of the percentage of GDP affected because of floods, I think India comes last year. It's just only 0.84% of the say GDP. And that's because most of other countries are very small countries. But if you look in terms of the absolute value of the money that is affected or GDP that's affected because of floods, it's almost $14,317 billion per year. Okay, so it's quite significant. And similarly, in terms of population exposed to floods, again, there are 15 countries, as I said, are the top countries which face the problem of this frequent flooding. And 80% population exposed to floods are actually from these 15 countries, and India is the top in that, with 4.84 on average millions of people getting affected on average, which is higher than the 4.24 billions, which were the people affected because of floods or across other countries other than these 15 countries. And if you try to observe the number of recorded natural hazards as well as natural flood events, you find that they have been increasing over the last few decades. There's number of events are increasing, and one of the reasons attributed for this is the climate change, global warming and climate change. And in terms of among all the four major, say, natural disasters, hydro disasters, more predominant one, especially India, you can see that more. In fact, among the four, this is the say highest to this point. And similarly, if you look at across the world, if you look at the top 20 countries which are most vulnerable for floods, in terms of the GDP of that city being affected, I think out of 20, I think 17 countries are from the developing countries, and 3 of them are from India. Say Mumbai, the 7th position, and Kochi and Surat all are on the western coast. So the coastal line, the western coast is frequently affected by cyclones and then severe rainfall. So these are the coastal cities are affected by the floods. But okay, there are many cities which are frequently affected by floods, but I'm talking about the top 20 cities in terms of the say average annual losses that are occurred by these things, because these are major cities, and so these cities are incurring huge, almost more than 0.25% of local GDP as losses per year, and they've come under the top 20 countries, 20 cities of the world. So in summary, I can say flood is a very common and widespread natural disaster, especially a country like India. And as per the estimates of Central Water Commission made in 2010, the annual losses are approximately around 1,800 crores per 1,800 crores. And the IPCC 2007, in fact, the recent IPCC also says the same thing. The floods are expected to, floods and other natural disasters like droughts, also extreme weather, droughts and other things, are expected to occur more frequently, and it can become more catastrophic. And in fact, I've shown the statistics earlier that this is in a way true, because if you look at the number of flood events that are occurring over the last few decades, in fact, last few decades has been increasing, the number of this is rising. So what are the causes of flooding? Okay, so try to visualize as I consider the different types of causes for flooding. One is heavy rainfall. Because of various reasons, they say maybe certain pockets of the country are subjected to heavy rainfall, and this heavy rainfall causes flooding in that region. Okay, and especially this heavy rainfall, the intensities of this heavy rainfall is increasing in the recent time, especially in urban areas, and causing more floods in urban areas. And then, okay, a country like India is very frequently subject to cyclones. Both the east coast as well as west coast subject to cyclones. So cyclones can also cause flooding especially in the coastal areas. And so they usually lead to what we call as a coastal flooding. And that's what happened in Chennai, if you recall, Chennai is subjected to a very severe flood in 2015. Mumbai every year is facing problems of this thing, coastal flooding because of the cyclones as well as heavy rainfall. And snowmelt is another major cause of flooding, especially in Himalayan regions in India. In fact, this is, I borrowed this from a study that was undertaken of the glacial lake outflow that occurred in 2014, August 2014, where Uttarakhand, a lot of areas got severely affected because of the flooding that was caused because of mainly because snow melt, which caused the outbursting of this glacial lake and started flooding large number of areas, and many people got affected by this. So this is maybe a study was done on this, and this is what I borrowed from that. So this is snow melt, especially in the say Himalayan rivers, is one of the also is cause of the frequent flooding. And in fact, the snow melt is expected to increase because of global warming, and that's also causing more frequent floods in this say states, hilly states like Himachal Pradesh or Uttarakhand. And though these urban floods are actually do not come under the category of other floods that I'm talking about. For the topic of discussion of this say training program is actually fluvial floods or river floods. But because I'm talking about flooding, I think floods also have become more frequent in urban areas. In fact, this is a picture taken from the flood that occurred in Hyderabad. A city like Hyderabad, actually, which doesn't have a major river also flowing through it, is now, if you try look at its past history, last few decades, you find that frequent flooding in that. And this is caused, okay, there are certain natural events like natural causes because of like it's being subjected to more frequent heavy intense rainfall, and because that's attributed to actually climate change as well as say urbanization. And the same thing is happening in cities like Bangalore or Bhopal and other cities like Delhi, New Delhi, and so on. But more is, I think, the more reasons for this flooding in urban areas like maybe I'm talking about interior cities like Bangalore, Hyderabad, and such cities, is more because of human causes. The reason of the rapid urbanization, encroachment of the water bodies, natural water bodies that were existing in this area, and then insufficient as well as inadequate maintenance of this drainage systems that we are constructing in these cities. Okay. Another human cause of flooding is a dam breach. So it's not so frequent like other kind of floods, but this also can be a devastating effect. In fact, there's a picture taken of the recent, say, dam breach that occurred in Maharashtra and Ratnagiri district in 2019. July 2019, which caused a submersion of large number of villages, and I think caused some loss of human life also. So these are the major causes of floods that's happening in especially in a country like India. And if you try to classify the types of floods, I think we classify them as different categories. What is natural floods, coastal floods. The coastal floods are caused because of tidal waves, maybe high tides or tidal bores, and so on. And but what I think, as far as this particular course is concerned, we are talking in terms of natural floods which are occurring in rivers, where floods related to rivers which are caused because of either heavy rainfall and torrential floods or fluvial rises, and maybe dam break analysis, I think, is also one of the topics that we covered in this particular course. So these are, I think, three types of floods that you're talking about. But floods also caused because of anthropogenic floods, like caused because of improper management of hydraulic works. That's one of the reasons attributed to the Chennai flood that occurred in 2015. Not only heavy rainfall, but also improper management of the water bodies that are existing there, and breaks and leaks in the water bodies and so on. With this background, let me just try to define the terms that we very frequently use when we talk about the natural hazards. One is we talk about hazard. So hazard is maybe I'm just borrowing a definition from a textbook: a threat or condition that may cause loss of life or initiate any failure to the natural, modified, or human systems. So flood hazard is one such kind of thing where, I say, it's a condition which is causing a loss of life, as well as can cause huge economical loss, as well as say loss to the society. Okay. No, there are different approaches to actually assess the hazard. But as for when you talk about the flood hazard, I think flood hazard has to be a probabilistic approach because the amount of damage that's caused because of flood is obviously depends upon the intensity of flood or the discharge, the peak of the flood that is happening. And this is not a constant, it varies. Even a particular location, it obviously you all know there's uncertainty, it is not a constant. So it's a probabilistic. Obviously, we have to use a probabilistic approach. That's what I'm going to talk about as we proceed further. How we deal with this flood approach and how we assess the risk based on probabilistic approach. So when we talk about flood hazard, obviously we need to talk in terms of the probability of it, the flood, a particular intensity of flood occurring, and what kind of damage it when. And obviously damage also depends upon this the intensity of flood, and thus damage also assessment has to be in terms of probabilistic approach. And once you identify a hazard at a location, we look at its vulnerability. How vulnerable is that area or that say that region for this particular hazard, like flood? When I talk about flood, so a set of conditions and processes resulting from physical, social, environmental, and economical factors which increase the susceptibility of the community to the impact of hazards. Okay. Now, when we look at the vulnerability, in fact, as far as flood vulnerability is concerned, we'll talk about three types of vulnerabilities. One is the economical vulnerability. Economical vulnerability is where you're looking at, say, the economical loss. Say, for example, a flood can cause a damage to the agriculture crops. So maybe a huge damage to, say, crop loss, or in a city like an urban area, it can cause a loss to property, or say it can cause damage to buildings. So all this could be, or loss to business. So these are something which are economical loss. So this is one kind of vulnerability. So what could be the possible economic? So in fact, for example, the top 20 countries which I showed, vulnerable countries, vulnerable cities that I have showed earlier, is it the vulnerable there we are talking in terms of economical loss, in terms of the percentage of GDP of that location. Other kind of vulnerability is social vulnerability. So the people, there's a population getting exposed to this hazard, and then there could be human loss of life, or loss of their livelihood, or maybe it will affect, say the people get, say they have to dislocate it, or maybe can cause a lot of nuisance for them because of the flooding. So this, all this could be a kind of other kind of vulnerability, or the social vulnerability. Okay, and then finally we have what you call as cultural vulnerability. Say cultural vulnerability in terms of say maybe could be loss of say maybe kind of heritage, say or ancient say locations and all such things. So usually we are more concerned, most of the cities or towns or most of the river basins, we are more concerned about the economical and social vulnerability, how that hazard is causing a loss to these two kinds of communities. And then finally, based on this, we have a hazard, identify an hazard, and then we assess the vulnerability of that location for this hazard, and then based on that, we evaluate the risk. The risk is obviously a combination of a function of these two, hazard and vulnerability. Like, what is the likelihood of a flood event causing a certain damage? So it's what we actually identify as risk, flood risk. Okay. So with these definitions, let me now go into the way we try to analyze the flood risk, or flood hazard and risk of any particular location in a river basin. Okay, maybe basically I'm talking in terms of river basin. Okay, so one is a probabilistic approach, as I was saying earlier. If you have the past records of flow data there, we use the frequency analysis, concept of frequency analysis, to assess the frequency of a particular flood occurring. So the frequency analysis is a process. I think many of you would have done this course in your say BTech or MTech, maybe say where you talk about statistical methods for the analysis of hydrological analysis, and then there you would have studied about frequency analysis. So where you try to find a relation between the magnitude of an event and its frequency. Okay, a relation that between the magnitude of the event and the frequency. In this case, we are talking about the magnitude of flood events. The magnitude of flood here, we talk in terms of discharge. So what is the discharge and the corresponding frequency, how frequency it occurs. So this is the this frequency analysis used to analyze any kind of hydrologic exchange, could be extreme rainfall, floods or droughts. Now, wherever we have the past records, say the river basin, you have gauge data, and then you can use the past gauge data and then use that data to do the flood frequency analysis, identify the flood magnitudes of different frequencies. In areas where you don't have flow data, in basins where you don't have any flow data, maybe we depend upon the rainfall data, and then as we'll talk about later as I proceed further, we'll use hydrological models to convert the rainfall data into a corresponding discharge and then do the frequency analysis. So maybe we'll be doing the frequency analysis either on the floods if you have the discharge data available, or if you don't have the discharge data, maybe you'll go for rainfall and then do the analysis of the rainfall, extreme rainfall. Okay. So what we do in the frequency analysis is we are trying to talk in terms of the relation between the magnitude and the frequency. Now, frequency in hydrology, we use the concept of return period. Again, this is something for what is not new for you. I'm just trying to revisit this definition so that it will be helpful for you to recollect what you studied in your hydrology course. So we talk in terms of return period. Return period is like in terms of the, what we call as I can define recurrence intervals. For example, if I talk of a magnitude xg as the magnitude of an event, a flood, for example, flood discharge. So we define recurrence interval as the interval between occurrences where the discharge was more than greater than equal to this value. So the number of time, say the time gap between two occurrences of that or two exceedances of that discharge. Okay. And so return period is the expected value of average value of the occurrence value measured over a large number of occurrences. So it gives us the average interval between say the two events or two consecutive occurrence of that event. For example, if I say a 10-year flood, what I mean by 10-year flood is a flood that occurs on average once in 10 years. On average once in 10 years means it's probability that, in fact, please note, when I say once in 10 years, it doesn't mean that if it occurred in 2021, it doesn't occur till 2031. It is on average, it occurs once in 10 years. But it's always likely to occur any year, and the probability that it occurs in any year, given year, is actually given as 1 by return period is equal to 1 by 10, that's 0.1. So this, I think, these are all fundamentals which you have studied in your hydrology that I'm just trying to review them. Okay. Just to give you an idea about what is this return period or return period, I just have taken the data from a location called Polavaram, where a project is being constructed on the Godavari. So I have that, say, I've taken the data from 1971 to 2013, and then picked up the annual maximum, the largest value from each year. What I have is the daily flow data. So from the daily flow data, I picked up the largest from every year, and then plotted that data. So this is the annual maximum flow at Polavaram. And then, now for example, if I take a value like 40,000 metric cube per second, I'm sorry, the units are not mentioned here. All these values are discharged in metric cube per second. I'm sorry for that. So this is 40,000 metric cube per second. If I take this value, you see, you count the number of times this value has been equal or exceeded. Okay, so if you count that, I think over these 43 years, this 40,000 metric cube per second has exceeded 10 number of times. So I can say that the return period of this is 43 by 10, 4.3 years. That means this particular flood of 40,000 on average is likely to occur once in every 4.3 years. But please note that 43 years data is not a large enough data to actually say this. So there's only a kind of empirical method for estimating return period. I'll talk about the analytical method for estimating return period, where you use the concept of probability distribution and things. So I can say probability of exceedance of this 40,000 metric cube per second. Towards the probability that a particular year this flood of 40,000 be exceeded is as 1 by 4.2 is 0.23. So how do we do this analysis of flood frequency analysis? Okay. So I need the data, the past flow data. Now, I just gave an example of Polavaram just now, where I picked up the daily flow data. So usually in any gauging site, you have data measured on a daily basis. On average, you get that average say flow every day. So the Central Water Commission or any organization which is measuring the flow at the gauging station normally measure the flow on a daily basis. So Let's say I have the data of the past records of the flow measured, the location, the daily flow. So we call that as a complete duration series. For example, at Polavaram, I have daily flow data measured from 1971 to 2000. Okay, what I showed is 2013, but I have up to 2018. So say 48 years of data, 48 into 365 days. That's the type of data that I have. So if I consider the total data, this is what you call as complete duration series. I'm talking about daily flow over 1 year is 365 days, but over 40 years or 45 years or 50 years, whatever is the length of record that you have, if I take the total data. But please note that with this data is not the extreme value, because what we are interested is only flood frequency analysis, where I'm talking about a flood event. So flood event is an extreme event. So you don't find the floods occurring every day. So most of the time, the daily flow data, you have a normal flow. Only certain time of the year, you get the flows increasing and causing a flood. So obviously, we're not interested in the everyday flow. So I'm interested only to pick up the extreme value. So how do you pick up the extreme value? One way is what I just now showed. Pick up the largest from each year, and that gives you what you call as annual maximum series. That's what I have just now showed. The previous figure that I've showed is what you call as annual maximum series, where we pick up the largest value from each year and then take that series for analysis, for the analysis to find out return period or relation between return period and magnitude. Okay, so there are arguments against this procedure because you're assuming that there'll be only one flood event in every year. Okay, that's why you're picking only one value from each year. And the largest of 1 year could be smaller than the second or third largest in some other year. So not necessarily that every year you are going to have a flood, and some years you don't have flood, a severe flood event, but still you are picking the largest value, which not been a flood event at all. So these are the arguments against this procedure. And so what people suggest is, okay, other procedure where we can do is you identify a threshold value. Okay, any discharge above 25,000 metric cube per second, I'll consider as a flood event. So pick up 25,000, identify all the events, all the days on which the flow was more than 25,000, and then consider that as a series, a flood series, flood data. So this is what you call as partial duration series. But the problem here is the number of values that you're going to pick up may not be equal to the number of years of data that you have. Whereas when you're picking up only one value from each year, it is like, say there'll be, if you have 43 years of data, I have 43 value. But here it could be less than 43 or more than 43. And that constant return period that I explained to you in the previous figure may not be valid here. I need to translate that in terms of year, because the gap between that may not be a year, it could be less than a year also. Gap between two events. So to avoid this confusion, okay, someone suggests that you pick up threshold in such a way that you will have the number of exceedance over the threshold exactly equal number of year data that you have. It's called annual exceedance series. Now, so I may use either this series or this series or this series to do the frequency analysis of floods and then find out the flood risk at a location. But which one should we use? Okay, there are a lot of studies, research, and arguments, debates, and all those things happened over last few decades on this. And in fact, it's found that people have studied both these methods. When your interest is small return periods like 2 years, 5 years, or 10 years, like what usually you're interested in urban areas, then this method is better. But when your interest is a larger return periods like 25 years, 50 years, 100 years, and so on, there's no much difference between these two methods. And so it's easier to use annual maximum series. So most of the time for flood frequency analysis, we go for annual maximum series. But when you are looking in urban area where your interest is small return periods and you are trying to analyze the extreme rainfall in urban areas, we go for partial duration series. Okay. And again, this is something which you already studied in your hydrology. There are different types of probability density functions, so probability distribution functions, which used to say fix or analyze the data that you have. You try to fit a data of a distribution, and these are some of the commonly used distributions that we use in hydrology. One is what we call a general extreme value distribution, which actually is a 3-parameter distribution, but when one of the parameters zeta is equal to 0, it becomes what is known as more commonly known as Gumbel distribution. Most of you have studied Gumbel's method of flood frequency analysis. So this is what you call as Gumbel's equation, Gumbel's probability density distribution function. Please note that what they give is probability of non-exceedance, means 1 minus probability of exceedance. That's what you are looking at, is probability of exceedance. So this is one. And say log Pearson type 3 distribution is another commonly used distribution. In fact, US is a standard distribution that's used for all flood frequency analysis. That's what is done in US. In India, we more commonly use Gumbel distribution to do the frequency analysis. And then other thing is log normal distribution. So, but there are many more other distributions also. I'm not going to details because they're all what you would have studied on hydrology if you had undergone a course in hydrology at your graduate level. You would have done this course on, say, frequency analysis, and you have discussed about different types of distributions about this. Okay, so whichever distribution you're using, what you are trying to find out is, we are trying to find out a value of xt, which is having a, say, probability of exceedance equal to 1 by t. Probability of exceedance means I'm talking about the area under the curve on the right hand side. The area on the left hand side is what we call as probability of non-exceedance. Okay, so we're trying to find out the value of xt, which is having 1 by t, where t is written. So there are different methods. In fact, we use what is known as Chau's equation to say x bar is xt is equal to x bar plus some kt into s, where kt is called frequency factors. And so there are frequency factor tables. So depending on distribution that you're using for a given return period, you can find the kt value. And you know, from the historical data that you have, you can find the mean and the standard deviation, and then find out what's the value of xt for a given return period. Or we can find analytically, like for example, I'm giving for this general extreme value distribution. In the case of your Gumbel distribution, you can say mu bar plus sigma into minus log of minus 1 by t, where p is equal to 1 by t. Okay, so this is how we do the frequency analysis. And then based on this, what we try to do is, okay, we try to get the flood data, and then that is from the discharge data, we pick up the flood data like annual maximum series, and then try to fit a distribution like a Gumbel distribution, and then analyze it and find out for different return periods what is the corresponding magnitude. And then this is how we can find out the frequency of a particular magnitude of flood occurring. But what we are interested in is analyzing the damage or vulnerability of that, say, what is the damage caused by that particular flood. Okay, so from the frequency analysis, what you are trying to get is a curve like this, where you are plotting a graph between the magnitude of flood flow, and the exceedance probability. Okay, there's a flood flow and then the exceedance probability. So this is a graph that you get. Maybe once you do the frequency analysis based on the flow data that you have, and then you got this curve. Okay, and at the location wherever you have the gauging data, maybe there is a relation based on the local conditions there, or local discharge and stage you have measured, and you have got a stage discharge relationship in the location. So now I can convert a flood for a given flood flow. I can find what's the corresponding flood stage. So flood stage gives us the elevation up to which water will rise during that flood event. And now this will give us, if you, depending on the elevation and based on the topography of that area, we can find out what will be the area that's going to be submerged at this elevation. And you identify what are the properties or the, say, maybe the agricultural lands or property, or the households, the population that are exposed to that flood or that event at that elevation. So that maybe you may have to construct based on the local topography. You have to do a survey and then consider a graph between the flood stage and damage. Because what is the damage caused because of flood depends upon what was the water level during the flood event. So if you have, based on maybe the local topography, we can do a study and then consider a curve like this. For different stages, a low stage of its damage cost is less, but as the stage increases, damage cost is more. So if you have constructed a curve like this, and then what we can do is now these three curves will help us to consider a graph like this, which will give us a graph relation between the probability of exceedance and damage. So what is the probability of a particular damage occurring? So you can find out, for example, if I want to know for a given flood event, I can find the corresponding flood stage, and from the flood stage, I translate that into corresponding damage. And then for this flood event, I know what's the corresponding probability, so I can identify with what probability this damage will be caused. So this graph line that I have shown here, this will give us a relation between the damage caused because of flood against the probability. Now I'm talking in terms of economical loss or damage in terms of money, but I could have put this in terms of some other thing. Like, for example, I could have talked in terms of the population in getting exposed, maybe in terms of social value. In fact, I'm talking to the economical value, but I could have converted, because depending on stage, I can also find out what is the population getting exposed, how much population has to be, rehabilitated or have to be moved to evacuated, how many people will be affected. All these things also I can find out based on local conditions and then do a curve like this. Instead of damage, I can talk in terms of population exposed. But what I finally get would be a graph like this: damage, cost versus profit. So if I integrate or find the area under this curve, that gives me what is the average loss caused because of floods in that area. So I can find in terms of average losses that occur in that area, or I can try to find out the probability versus damage caused because of floods. So I can assess the damage caused because of flood event if based on the frequency analysis. So you do the flood frequency analysis, and then you need to have the data about flood stage versus flood discharge, and then maybe based on the local survey, construct a curve like damage versus flood stage, and then this will help us to construct this curve. So this is how we can evaluate the losses that occur because of flood in a particular location, if you have the past flow data. But unfortunately, it's not always possible. In every river basin, you don't have flow data, maybe you don't have discharge data, and such locations, such cases, maybe this method doesn't work, because only if you have flow data, maybe you will be able to do this. What we'll do in this, for example, a city like Hyderabad, for example, I want in a particular location, Hyderabad, I would like to assess damage caused because of flood. So I don't have flow data in a city like Hyderabad, because though there's a river flowing through the city of Hyderabad, it's not gauged in the city of Hyderabad, and then there are no flow data available. So in such situations, we depend on rainfall, and from rainfall, we translate that into this thing. So we need to depend upon hydrological models. So the hydrologic models are used for estimating flow hydrographs of rainfall. So what we're trying to do is, these hydrologic models help us to transform the rainfall data into the flow data. So typically, when a rain occurs on a catchment like this, a river basin like this, there'll be the rainfall will start falling on the land. There'll be, I know from your hydrology, you know, there'll be infiltration. Part of the rainfall will go down as infiltration, and then a part of the infiltrated water will start flowing laterally and may enter the river channel or drain here, and this is a discharge that's occurring here. So part of the flow will take place as overland flow. After it meets the infiltration, the water will start flowing down the slope and then go into the river basin and start moving. Okay. So there are different processes taking place in this hydrological cycle. So hydrologic models try to simulate these processes mathematically and then do the say analysis. So for develop or transform the rainfall into the corresponding discharge flow hydrology. Okay, there are different types of hydrological models, but I'm not going to again detail to types of hydrologic models and then exhaustive classification, all those things, because that itself will take a lot of time. But from the point of view of this particular discussion that I'm discussing about here, broadly I talk about a classification which is like, you may say the hydrological model could be a lumped model. A lumped model is where, for example, if I take a basin like this yellow shade basin, okay, the rainfall in this basin may not be uniform, or let's say soil characteristics may not be uniform over this, because soil characteristics are important because of the infiltration, or land use characteristics may not be uniform. But I'll assume that I'll just take the average condition of the entire basin and assume, say, for example, a single rainfall event over this, a single rainfall measurement, like I'll take the average rainfall over this entire basin. And then similarly, all the characteristics, I'll assume that they're constant over the entire area. So the lump, it's called, this kind of model is called a lumped model. Obviously, it's got its own disadvantages because hydrological, say most of the hydrological characteristics of the process are highly spatial, varied spatially. So this is one of the limitations of the model, but still lumped model have been used and then still existing use, especially in say because they're more easy to use mathematically and thus can give us a quick assessment of flow data and all those things. The other side, we have what we call as distributed models, where we divide this entire basin into smaller units, and then maybe, for example, today, most of the hydrological models that we are using are grid-based. We will divide the entire basin into grids, and then consider each grid, you may the rainfall can vary. The characteristics, hydrological characteristic also can vary. So that's all. That's kind of where you consider the spatial variation of the data, so rainfall as well as the hydrological characteristics, hydrogeomorphological characteristics. We call this a distributed. Okay, and there are a lot of such models existing today, which I think some of you may be familiar. Those who are working in hydrology would have used one of these models in your studies. For example, one of the very popularly used model is soil and water assessment tool called SWAT, variable infiltration capacity model, VAC model, watershed simulation and forecasting system, soil and water integrated model, watershed modeling system, stormwater management model, reservoir modeling system. Most of them are what I listed. Most of them are actually open source software, so that you can download them, and you have a lot of, for example, these two are very popular used models, and then you easily can find the manuals for this and learn them and start using them. The stormwater management model is basically for urban areas. It's, as the name indicates, a stormwater management model. It's meant for, say, design of drainage system in urban areas as well as hydrological modeling of urban catchments. Okay, so we can use one of these models provided you have sufficient data to do this and then develop. So, as I just now mentioned, the hydrological models translate the rainfall event into a runoff event. Okay. But that's not sufficient for us to actually develop a maybe flood hazard or flood assess the flood hazard and all those things. We have to integrate now, couple this with what we call as a hydraulic model. So what a hydrological model does is only gives you the discharge based on the rainfall that occurs. So maybe a flow hydrograph. What's the discharge and how it varies with time over in this thing. But so for example, if I consider a channel like this river basin. So once as long as the flow is confined within the banks of the river, the flow is one-dimensional, and then maybe you need to model this flow, how it propagates over this channel. And so we need to have some kind of hydraulic model which will study the propagation of this flow in the channel. Okay, but once this, say, the discharge starts increasing, exceeds, and then this rain, the cross section starts overflowing, then it starts spreading over the area, and so that also there it starts inundating the surrounding areas, and then it starts spreading. So that's how the flooding takes place. So if you really want to understand the say this concept, the flooding process, I think a simple hydrological model is not sufficient, because you need to start studying how this flood is propagated to the channel and when the overflowing takes place and how it starts spreading over the area. So if you want to understand the velocity, the depth of flow and all such things, because they are important from the assessment of flood hazard and flood risk point of view. The reason why we need to use hydraulic or what you call as hydrodynamic models. What they do is, maybe most of these models are basically models which study, which model the unsteady non-uniform flow taking place in a free surface flow. It's kind of free surface flow. Now the question is whether this hydrodynamic model is one-dimensional or two-dimensional. Say, as long as the flow is confined within the banks of the channel, like what I'm showing here, I can treat this as a one-dimensional flow because it's taking place along the length of the channel and becomes one-dimensional. So I just, a 1D model would be sufficient for me. A one-dimensional model is sufficient. So there are different one-dimensional models which study the flow pattern as only one-dimensional flow. So they study the flow within the drain and then study how the flood is propagating through the drains. For example, I talked about stormwater management model, SWM. So SWM just basically is a one-dimensional model. So it assumes that the flow is entering into the channel and then drains through the drains. It is a one-dimensional. But once it starts overflowing over this channel, then it starts spreading over the land. Then I cannot treat this as one-dimensional. So in that case, maybe the flow becomes a two-dimensional. So we need a two-dimensional. In fact, a better one would be, for example, if I consider a system like this, the flow is taking place. There is an overland flow, which is basically a two-dimensional flow, and then this is a one-dimensional flow. So what you require is a kind of coupling between a two-dimensional flow and a one-dimensional flow. A two-dimensional flow which actually models the flow over the floodplain, and a one-dimensional flow which models the flow in the channel. So that's what today we try to make use of what we call as 1D, 2D coupled hydrodynamic models, which try to integrate a one-dimensional model with a two-dimensional model, so that it will help us to actually study the propagation of flood and then generate what we call as flood inundation maps. So which will help us to understand what's the spread of the flood at a particular location and what will depth of flow at different locations, to what extent the floodplain is getting submerged, and that will help us to assess the damage caused because of flood and then talk about the vulnerability or risk of the flood. Okay, so that's what we have, and there are a number of such. Say this is what happens in the case of 1D, 2D. This thing, as long as the channel is concerned, it's considered as one-dimensional flow. But once the channel starts overflowing, it starts becoming two-dimensional flow. I'm just showing an example of an urban area. In urban area, the linking between the one-dimensional two-dimensional flow occurs at the manholes. But a river, it occurs complete continuously, because a river, it's like the overland flow can enter into the river, or from the river it can overflow outside into it at any point of time. But in the case of urban areas, because they're not linked at every point, they're linked only at the manhole. So maybe these node points are the points where there's a linkage taking place. Okay. There are several such hydraulic models. One is, as I said, SWIM is it's both a hydrological model as well as hydrodynamic model, but it's only a one-dimensional model. In fact, an extension of this SWIM is what is known as species SWIM, which is a 1D, 2D coupled model, but it's a commercial package, whereas this is a open source software. This is a commercial package. As far as riverine floods is concerned, we have models like HECRAS, SOBEC 1D, 2D, Flow 2D, LISFlood FP. So they're all useful for hydrologic modeling of river floods. And HECRAS is an open source software, and it's more popularly used for generating flood inundation maps and then use them for assessing the flood damage. Okay, SOBEC 1D, 2D is other popularly used model, but it's a commercial software. In fact, I have not listed other major commercial software used across the world is MIC package, which is I have not listed here, but Flow 2D is also a commercial package. LISFlood is again a open source software developed in European and mostly used in European Union for the estimate floods. Okay. So now I'll just try to explain to you how we use this hydrological and hydrodynamic model to assess the flood and then generate a flood inundation map, and then based on that generate maybe a flood hazard map. Okay, I'll take a case of an urban area, city like Hyderabad, but whatever methodology I'm explaining here is useful even for an urban flood also. So I'm just showing a typical flow chart, how this kind of modeling is done. Okay, so we have, in fact, I'm showing a one because what we use, I'm trying to show here, we use HHMS, but this HHMS could be replaced by any other hydrological model. Maybe if you are comfortable with SWAT, you will use SWAT, or you will use VAC or whatever it is. You need to have a rainfall model. We have used HHMS. So we have, say, we need the inputs for this will be the basin characteristics derived from the various data that you occur for the river basin in terms of catchment area, maybe elevation, distal elevation model, the land use pattern, and other characteristics, soil characteristics, all those things. And then obviously rainfall data in terms of rainfall hydrograph or such kind of data. And then you run the hydrological model, rainfall model, and then generate the, at the say maybe at critical points, junction points or very critical points, you generate the hydrographs or stream flow hydrographs. Now these hydrographs now have to be routed through the river basin or river channel, and that's where you use HECRAS 1D, 2D model. Okay, 1D actually does the flow routing in the channel, river itself. So you need to know the channel geometry, the river geometry, and other flow parameters, like for example, the reversed equation of channel and such things. And then the 2D would be basically to study, study the propagation of flood over the land, means over the floodplain. So the 2D obviously need to have a 2D digital terrain model, and then use some kind of mesh array to generate, to divide this into mesh, 2D mesh, because what this hydrodynamic models use is a finite difference method to solve these equations, and then define the boundary conditions, and based on that you can try to generate this, and then use some kind of mapper, maybe some kind of GIS facility to actually map this this thing and generate what we call as floodplain maps or flood inundation maps. I'm sorry for the spelling mistake here. It's floodplain maps, and generate the flood inundation maps. So I'll just try to show this procedure through a case study that we have done for a city of Hyderabad. This is the city of Hyderabad, and these are the different zones into which Hyderabad city has been divided into. This is the Musi River flowing through the city of Hyderabad, and based on the drainage characteristics, divided into a number of zones by Municipal Corporation of Hyderabad. So the study that we have taken up, what I'm going to show is for this area. This is one of the largest zones, Zone 12, and highly populated area, and in fact one of the major commercial areas of the city of Hyderabad, where a lot of commercial areas like Kukatpallis, Amirpet, Pekampet, all these areas come in this, and one of the areas which gets frequently affected by floods. So this entire area drains into the lake that's in the center of the Hyderabad city, which is Hussain Sagar Lake, and overflow from Hussain Sagar, which finally joins to the Musi River. So this is the zone that we have taken. So there's a land use land cover map of this city, which is based on 2016. You can see this entire red zone is the built-up area. It's highly densely populated area. So say in fact we find that it's mostly urbanized, except the upper parts where still you have some barren lands. But in fact, I'm not showing this here, but when we studied the land use changes, we find that this area got rapidly urbanized when compared to what was 2005 earlier. It was not that much urbanized. And you also find that there are small water bodies spread over this. But in fact, again, if you like to look at the old land use patterns here, you find that many of these water bodies have been encroached upon. The aerial extent of this water bodies decreased, and some of the water bodies completely disappeared. Okay, this is land use pattern, and then the area of this is 143.7 kilometers square. And what I'm going to show here is, though we did the simulation for different rainfall events, I'm going to show for one of the major rainfall events that occurred in Hyderabad city. It was in August 2008. In fact, I'm using this data for simulating for the land use pattern of 2016. In 36 hours, just a span of 36 hours, and around 220.7 millimeters of rainfall has occurred, and this is how the rainfall was spread over, say, the vegetation here. There are different spells of rainfall, and the total rainfall was 220.7 millimeters in 36 hours. This is a digital terrain model showing different elevations. So this is lowest elevation. This how this is the data that we use to do this. So now, in fact, we use the flowchart that I showed as a procedure we use. We use HMS to actually generate the flood hydrographs, and then these flood hydrographs were routed using Recurrence model, 1D, 2D coupled model. And then this how at different spans of times, this how the flooding, you can see how the flooding slowly starts, how the areas get started flooding. So in fact, initially, I think there's no, the entire area is clean, but slowly you find that this area starts, water starts accumulating, and the water starts spreading. And finally, you find that these are the areas which are getting flooded. All along this portion, the blue portion is the area which is getting spreading. So that's how we can actually, I'm not showing animation because that takes a lot of time, but we can actually do animation and then simulate this and then find out how this is it. And I can superimpose this over the Google map. And so you can see easily what are the areas which actually got affected by this flood. So all these areas, in fact, say in fact dark blue means the fermentation is. Excuse me.
But in Kabaddi, what is important is you have to be calm. So it is.
Hello. Hello.
I am muted.
Okay.
Please continue.
Okay. yeah. Right. So this is how the say I can generate the flood inundation maps and then superimpose the areas so I can find out easily, identify with the areas which are getting flooded. Okay. Now this is one aspect. So what we now generated is the flood inundation maps, and this okay. The secondary data that we get from this kind of analysis is I can at every location I can find out what's the depth of inundation, because what we did is a two-dimensional model. The two-dimensional model will also give us the depth of flow at every location and also the velocities at those locations. So I can make use of this kind of data in order to actually do some kind of assessment about the hazard. So maybe because I'm talking to urban areas, in urban area, the flood hazard depends upon, so flood hazard I'm talking in terms of the social hazard, or not in terms directly to property, but I'm talking in terms of social hazard. So the effect of the flood on the human or the society depends upon both the depth of inundation or depth at the flow at that location and also velocity. So we use these two in order to define different indices, index for flood hazard risk. So what we did is like, okay, we consider the product of depth and velocity, which is obviously meter square per second. So when the depth of say if this is less than 0.3, means D is between depth of inundation is between 0 to 0.3 and velocity of flow is less than or equal to 1.5, and the product of these three is less than or equal to 0.3. This is not there's no hazard to anyone. It's a safe for everyone. But when this D becomes less than or equal to, say more than 0.3, but less than or equal to 0.6, means when your D is between depth of flow is between these two, and inundation depth is between 0.3 to 0.5 meters, but then the velocity of flow is still less than 1.5 meters per second. It is unsafe for small vehicles and children. And so Z zone 3 is when your D is less than or equal to 1, and depth of inundation is between 0.1 to 0.5 to 1 meter, and velocity is still less than 1.5 meters per second. This is unsafe for vehicles and people, but zone 4 is the most say vulnerable zone, where the D into D cross V is more than 1, and the depth of inundation is also more than 1 meter, and also the velocity of flow is more than 1.5 meters. It is also not safe for property, the structures, various type of structures that are existing in that area. So this is a kind of index that we try to use and then classify the different areas into different zones like this. So zone 1 is safe. So anything area is zone 1, but zone 4 is the most vulnerable area. So in fact, that's how, if you plot between depth versus velocity, this is how the zones will be classified. This is what we try to use. So based on whatever analysis that we did from that, we try to actually identify the vulnerable zones, or say the more zones which are having more risk. So for this, what we did is actually we tried to evaluate what is the, say, impact of climate change. Okay, this again another study that we did for Hyderabad city, where we try to investigate the impact of climate change on extreme rainfall, and then based on that we developed the different scenarios where we try to generate for different return periods, 2 years, 5 years, 10 years, and 25 years, the possible synthetic say rainfall hydrographs under different climate change scenarios like RCP 2.6, 4.5, to 6 and 7.5. That's 4 different future climate scenarios, and this will be the rainfall synthetic hydrographs that we have constructed based on the study, other study that we did on the extreme rainfall Hyderabad city, and then study the impact of climate change on the rainfall, extreme rainfall. So we try to use the same process, a HHMS-based hydrological model, and then HECRAS 1D, 2D coupled model to generate the flood inundation maps. And then based on the velocity and depth of inundation that's taking place, we classified the different areas into different zones, zone 1, zone 3, and another one. And then develop this kind of flood hazard risk for say under different climate change scenarios for this. So for example, this is for say 2 years return period flood. This is how the flood hazard zone is. The dark red is areas which are in zone 4, which are the most vulnerable areas, or more flood prone areas. So in fact, if you look in terms of areas, so this is how it has been. So you find that the future, in fact, as under different climate scenarios, in fact, RCP 8.5 is the worst possible scenario for future climate change in terms of, say, emissions, greenhouse gases. Find the area under zone 4, though it's not that significant. So 0.13 square kilometers under 2.6 and 8.5 is 0.88. This is once in 2 years. 0.88 kilometer square area is going to get affected, going to come under zone 4. Or 1.11 square kilometers of this area is going to come under zone 3. And that's how what we can have. And same way I am showing for just 5 years also. This 5 years return period for different, again, this thing. You can see that this red areas are actually started increasing and compared to for 2 years flood. So if you, again, look at the areas, you find the zone Z4 under this RCP 8.5 scenario, 1.15 kilometers square is the area which is subjected to more severe flood damage in under this scenario. whereas the other things are like this. So in fact, I have maths for other things also, but just for saving timing, I'm not going into those details like this. But this how here I'm talking, because upper area, I'm just talking in terms of velocity and depth of inundation based on the development index. But what is the hazard index that you use depends upon what you are trying to, what you are interested here. So in the case of, for example, river floods, when you are looking at agriculture lands, you try to find out what is the type of crops that you have grown. Maybe you'll do a survey, and then maybe the similar kind of index you can develop in terms of depth of inundation. Maybe velocity maybe or may not be important, but depth of inundation may become important in terms of agriculture lands. So what is the extent of crop loss that can occur? And what types of crops are being grown. So maybe similarly, you can develop some index like this. So depending upon the your interest, what is that you are looking at, what kind of damage you're looking at, you can develop some kind of index to evaluate the hazard or vulnerable, say, risk, and then develop the risk maps like this based on the hydrologic and hydrodynamic models that we have done. Okay, so just to conclude, I'll just try to summarize what we discussed about the last 1 hour. I just try to give a quick overview. Obviously, a 1 hour is not sufficient for me to go in depth and this kind of study on flood risk assessment and flood assessment, but I just try to give an overview of how we do this flood risk and flood assessment using the hydrological and hydraulic models. Okay, so but what I did touch upon here is no, flood, we are talking about isolated floods. Like flood is not an isolated event. Flood actually could be our multi-hazard phenomenon, because there could be compound effects, especially in, for example, in the case of your coastal areas, there could be a riverine flood. At the same time, there could be a tidal surge, a storm surge taking place, or a tidal surge taking place. So it could be a combined effect of flood, riverine flood that we are talking about, and also tides. This can happen in coastal areas, like, for example, Mumbai or Chennai. These are the cities which are even Visakhapatnam in Andhra Pradesh. These are cities which are subjected to this kind of hazards, where it's not just a flood. When a flood occurs, there could be a kind of other extreme natural hazard also taking place. So there will be combined effect of these two. So we talked about the riverine flood, but I think we need to go for that kind of multi-hazard phenomenon. Or it could be a coupled effect. For example, in hilly areas, say there is a flood, and same time there could be a landslide which also can aggravate the problem there, because of extreme rainfall in the hilly areas. There is a flood occurring taking place, and then that be coupled with a landslide because of heavy discharge. Maybe the landslides can take place, and that could actually be a coupled effect taking place. So it's again a multi-hazard phenomenon. Or there could be application effects, like say, for example, the application could be caused because of a heavy rainfall occurring and the flood caused, and at the same time the upper, like that's what happened in Chennai 2015. Like you have reservoirs, upstream reservoirs which have become full, and then you have started releasing water from there, and at the same time there's a flood taking place here. So this could be a kind of application effect or a cascading effect. So all this, I think we need to, unfortunately, there are not many studies which have been done on this kind of multi-phenomena. Means you consider this as multi-phenomena, especially in a multi-phenomena, multi-hazard phenomena, and then evaluate the risk and hazard. So I think this kind of studies are needed, especially in hilly terrains, like example, Uttarakhand, Himachal Pradesh, where this kind of things can happen, even some parts of Kerala also. And similarly, in coastal areas, coastal cities like Chennai, Mumbai, I think we need to have this kind of things. And another aspect I think we need to look at when we are doing this kind of flood risk assessment is there is a lot of uncertainty. So I think we have to deal with uncertainty, because many times, say, people lose the faith in our models because our models are not perfect. So, for example, I said about hydrological model and then hydraulic model, hydrodynamic model. So these models, based on that, I developed this model. But what is the guarantee that the predictions that I've made based my model studies are correct? So this could be uncertain because your models are uncertain. So that uncertainty also has to be taken into consideration. There must be a kind of, how do we tackle this uncertainty? Okay, experienced modeler can maybe reduce uncertainty, but still there is always an uncertainty. So how do we account for this uncertainty, and how we assess uncertainty is also an issue that we need to be looking at when we do this kind of assessment. And as I just mentioned at the beginning of my talk, there is this flood risk or any natural hazard risk is expected to increase because of climate change. So climate change obviously going to cause more frequently this kind of hazards and then also become more severe and more catastrophic. At the same time, you find that the rapid urbanization across the country and rapid deforestation, say they're also causing an increase in the flood risk. Say, maybe one of the reasons in elite Himalayan regions for more frequent landslides and then floods is, I think, encroachment of lands or forest areas. I think many of the, the urbanization, deforestation, these are, I think, what are being attributed for more frequent occurrence of landslides and then hazards in the Himalayan regions. So I think this is other thing that can lead to more multi-hazard phenomena. And there's, I think, something we need to look at it and see what is the impact of this human activities on this. And obviously, we need to develop a technology or methodologies, tools, which will help us to assess this flood risk under climate change in a better way. And so there's, I think, something where a lot of research is still going on and a lot of people are working on it to develop, improve the methodologies that we're using and to improve our understanding of the flood risk and then assessment of flood risk. So with this, I conclude my talk. I'm sorry, I just exceeded my time from 11 to 11:06. So thank you all. And if there are any quick questions, we can have. Otherwise, I'll conclude.
Thank you so much, sir, for a very informative lecture. So I hope our participants like this lecture. And if anyone have any query, he or she can directly interact with Professor Uma Mahesh, sir.
Yeah, good morning, Umesh sir.
Yeah, good morning.
Yeah, thank you very much for the wonderful, informative, and practical session. Yeah, I have a question like, can you please tell me about what are the parameters and the process we need to consider while integrating hydrologic model with hydraulic model?
No, okay, hydrological model with hydraulic model. Hydrologic model will give you flood hydrograph of different locations. So what you are trying to do when you are linking with hydraulic model is you are using some kind of flood routing. I think you would have studied flood routing in your hydrology. The only thing that you need the type of data. If you are looking at only one-dimensional model, usually flood routing in a channel, you need to have channel geometry and then channel characteristics and then maybe rugosity coefficient and such things. And so you need to have that. But when you go for two-dimensional model, obviously you need to have the floodplain, the flood, like I was said, digital error terrain model, and then the land use pattern there, and based on that, say hydraulic characteristics like rugosity coefficient, etc. So all this kind of information required, and how effective your model, how well it predicts your this thing depends upon your data that you can get, and also. Most of the time, you don't have proper data to validate your this thing, and that's another problem that you're going to have in this kind of thing. Yes.
Yeah, thank you, sir.
Thank you so much, sir. Our next speaker, Professor Haji Ajmatullah from University of West Indies, Trinath. Sir has already joined the meeting. Hello, Ajmatullah, sir. So, sir, can I? Sir, your voice is breaking, sir. Sir, your voice is breaking, sir. Sir, Ajmat, sir.
Hello.
No, not audible, sir. Your voice is breaking, sir. I think your internet is not stable.
Ajmat sir, if you could please don't open the camera. I guess it's taking more bandwidth. That is why we are not able to hear you.
Manish, am I audible?
Now,
Hello?
sir, you are audible. So, first, I want to
Okay.
introduce
I
Ajmatullah,
will
sir.
open some time for my video. Yes. Then I
Okay, sir. Sir, now first I want to introduce you. So, Dr. Haji Ajmatullah, sir, is Professor of Civil and Environmental Engineering at University of West Indies at Trinath. He has degree in Civil Engineering from SKD University and Master's degree in water resources from Devi Ahilya University and a doctoral in hydraulic engineering from IIT Bombay. His research interests and activities are in field of physical hydraulic model studies, water resources engineering, and hydroinformatics. He has authored more than 100 peer-reviewed journal papers and book chapters. He has guided 7 PhD students and 25 plus master's students. He has been a member of the editorial board of several high-ranked journals like Water Science and Technology, Water Supply Journal, Journal of Pipeline System Engineering, ALC, Dam Engineering. He was also the associate editor of Journal of Hydrology. So now I request to Professor Ajmatullah sir, please start your lecture, sir.
Thank you, Dr. Manish. Thank you, Dr. Manish. Am I audible?
Yes, sir. Please continue, sir.
Yes. Good morning to all participants and NIT Warangal Department of Civil Engineering. Today I am going to talk about application of soft computing techniques in hydraulic engineering. Next slide, Dr. Manish. The outline of my presentation today. Next slide, please. Yes. Some introduction of the spillways and score. And some techniques and phase. You can see in this picture. After my master degree, I joined Central Water and Research Project, Khadakwasla, Pune. This is the Dolianga hydroelectric project, and I think Uttarakhand. This is spillway. Right, clear. This is 1:70.
Sir, your voice is breaking, sir. Your voice is not clear.
Now, Dr. Monish.
Now it is okay, but sir, in between, it was not clear, sir. Hello, Ajmal, sir.
Yes. Hello.
Your voice is not clear, sir.
Okay. Give me 1 minute. I will use my.
Okay, sir. Okay.
Hello.
Yes,
Can
sir.
you hear me, Manish?
Now it is clear, sir. Now it is clear.
Yeah. Sorry, the internet. So this is you can see picture. One of the hydraulic model which I have done very first model in Central Water and Power Research Station, Dholianga model spillway, 1:70 scale model, geometrically similar model, 3D dimensional. This is Rockfill Dam. You can see, yes, you can see my left hand side the model and right hand side. This is the one of the classical example of Rockfill Dam. natural hazard. You can also see we have suggested after several times. Here, what will happen? The jet hits the right bank, and the right bank may collapse. So we have suggested the deflector. You can see, some 20 degrees deflector. So water uh, sprays and energy dissipation happened. So some part of natural hazard we have saved the right bank. Okay, you can see exactly another thing. You can see upstream, like, in 2009, I think 2009 and 2013 Uttarakhand, several floods. So you can see this is the situation there now. Currently, I don't know. Okay. Yeah, see the another example, Salal Dam spillway in Jammu and Kashmir, which is after the bilateral agreement with Pakistan. Okay, Salal Dam spillway in Jammu and Kashmir. It was completed in 1987. What happened? Operation of one day spillway operation, right bank. Next slide, please. Yes, this was discharge.
Sir,
This was
again your
discharge.
voice is breaking, sir.
Hello. This was discharge. This was discharge. Hello.
Sir, again your voice is breaking, sir.
Only no. Hold on 1 minute. Can you hear me now? Hello.
Now it is okay. Now it is okay, sir.
Okay. Okay. You can see Salal Dam spillway in operation. I'm using Wi-Fi. This is energy dissipated. They are provided skijam bucket in operation. You can see even jet, and you can also see fog. They don't see right hand side what is happening. So all powerhouse, everything destroyed within 1 day. This is another cause. Since we have maintained power generation of full reservoir level, this is up to almost 97 meters.
Sir, your internet, I think your internet is not
Hello?
stable, sir. Sir,
Yes.
your internet is not stable, I think, sir. Your voice is breaking badly. Hello.
Hold on 1 second. I will move 1 second. 1 second. Dr. Mani. Hello, Dr. Manish. Can you hear me
Yes,
now?
sir. Now it is okay.
Yes, sir.
But sir, once you will
Yes,
start, sir,
sorry.
it
I'm
will
really
again, I
sorry.
think. Okay, no issue, sir. Please continue,
Sorry,
sir.
sorry for the internet. Here due to rain. Sorry, Dr. Manish, due to rain here. Can you go back to previous slides, please? Previous slide, please.
Yes, sir.
So Salah completed in 1987. After inauguration, that time I really don't know with the Prime Minister. Within 1 day, with this much charge, all right bank situation you can see in power generation, everything. So this is the yes, this huge loss.
Sound is not clear.
Sir,
Hello?
your voice is not clear, sir.
Hello?
Sir, voice is not clear, sir. Hello?
Yes, Dr. Mani.
Sir, voice is not clear, sir.
Hello, sir. Voice is not clear, sir.
Yes. Hello, can you hear me now? Hello?
No, sir. Sir, still it is breaking, sir. Your voice is breaking. I think your internet
Again
is
breaking?
not stable, sir.
1 second. Dr. Mani. joined from with my mobile.
Hello, sir. Hello, sir.
Hello. Hello. He is rejoining. Please wait. Hello, Ajmat sir. Hello. Ajmat sir. Hello,
Manish, I
Ajmat
think
sir.
he's not there, I think.
No, sir. He has joined with another mobile. I think Ajmat Thula. Here it is showing.
Hello,
Hello.
can you hear me now?
Now your voice is clear, sir.
I changed. Sorry, I changed network. Okay, so
No issues.
this has happened in Salal Dam spillway. After this,
Okay, sir.
we have a learn big lesson from this Salal Dam spillway model. So you can see similar situation in Parvati Dam spillway in Kullu, Himachal Pradesh. Same thing. So you can go to next slide, please. Yes, you can see right hand side, all everything, banks collapse, powerhouse, everything destroyed. That time, Prime Minister, I don't know, he was very upset and very angry with NHPC. Yes, this is another project from Andhra Pradesh. Now in Telangana, Andhra Pradesh, Srisalam Dam spillway in Kurnool district. You can see the what problem here. They provided lip angle, very lip angle. We are now in plus to intermediate level. If 45 degrees, the jet will go very high. Here, I think they provided 30 degrees. So jet is very near. See, so I think every year score takes place. Now they are worried about this one due to dam safety concern. Okay, this is the okay, next slide, please. Hello, next slide, please. Yes, next slide, please. Dr. Manish. So this is about Srisalam Dam spillway in Kurnool district.
Hello.
Yes,
Hello.
next slide, please. Yes, You can see in case of Kariba Dam. So dam height 120 meter. The score takes place almost, you can see, in 80 meters every. You can see in 1981, 1970, 1962. So due to high velocity jets, score takes place downstream side. This is about Kariba Dam spillway. Okay. Okay. This so before do any projects, I have collaborated with Iranian water resource research, several hydraulic models with physical hydraulic modeling. They have conducted. They have also have very good laboratory like CWPRS. Okay. So spillway. So just now the professor has talk about flooding. So to passing flood in safety manner, dispose flood water in excess of reservoir capacity. So spillway is the main our main function to control the discharge using through gated operation. Spillways for flood control situations and power generation situations. But the only problem is the energy dissipator. Which one you provide, either chilling basin or ski jump bucket or something else. So efficiency of this dissipator, I'm talking about ski jump bucket. Okay, next slide. So you can see here in this picture. So here I am showing R is bucket radius and lip angle 5. So this one you can see score takes place downstream side due to high velocity jets away from which depends on velocity and bucket lip angle. Okay, score takes downstream of the bucket. To prevent uncontrolled score of riverbed, two alternatives you can see. Since if you provide most rate of change of momentum equal to 4, okay, this much force. So if you have high radius and lip angle, you can throw that very far from the main structure. To prevent pre-excavated plunge pool is one of the option. Another one is rising tile water level by constructing a weir sufficiently downstream side. Here, see estimation of score. So this is another theoretical analysis coupled with the laboratory analysis, laboratory investigation, theoretical analysis coupled with prototype observations, empirical relationship based on prototype observations and laboratory experiments. Okay. So factors considered to predict score depth, discharge intensity and head, tile water depth, lip angle of the bucket, radius of the bucket, particle size D50, rock quality designation, and rock mass rating. Several investigators, almost 9 decades, 9 decades, in awareness developed one formula using discharge intensity and head and other. Previous slide, Manish, Dr. Manish. Hello. Yeah. Damle in 1965 from Central Water and Power Research Station. They have considered, this is the main observation. You can see reservoir level 2, some considered up to lip angle, lip, that is head. Another awareness considered reservoir level to the difference between reservoir level to tile water level. So this is the only difference. So anyhow, they have calculated they have considered only two parameters, discharge intensity and head. But in my case, I have considered all these 6 variables. Later I show you, I have developed the regression equations based on my model data. I have conducted several experiments, 75 experiments during my research in Central Water Policy. You can see failure of formula. Bureau of Indian Standard and USBR small dams both recommended this fairness formula, which is 9 decades old, almost 9 decades old. Okay, then he considered discharge intensity and head, only 2 parameters. You can see in case of Wukai Dam, the observed score was 27.4 meter and prediction 18 meter. You can see in case of Rana Pratap Sagar, Kariba Dam. So all these formulas failed, but still, our Bureau of Indian Standards and USBR recommended this formula. Okay. Next slide, please. So due to failure of this formula, so the regression techniques, that time I have considered neural network techniques, few techniques. These are the few papers I have considered in my literature review. Okay, next slide, please. Yeah, I have used feed forward back propagation algorithm, which is input layer, hidden layer, and output layer. Another one, cascade correlation algorithm. Here, hidden nodes are keep on adding till you get target value output. And the radial basis function. Yes, radial basis function. Here you can see. Okay. Another algorithm I say neural networks like fuzzy logic and FIS. Here the 5 layers you can see. These are the memberships have used in the time. Later on, all this neural networks not give any option. So later I developed gene expression programming. So these are the some drawbacks. A large number of equations have been developed to predict score, but none gave exact value. Many equations I told they told for
Sir, again your voice is breaking.
another problem and several conditions. So many, so ignoring many effects is what I told. Less attention has been paid to. So there is therefore, so whenever problem is very poor, so even numerical models, my students have tried, but that's also giving only depth. So here I have considered plunge pool depth, width, and location of score. Okay, you can skip. So these are the importance I am showing about neural networks, why I have considered. Okay, so I also collected proto observation data with the discharge intensity and head. I have developed another equation for sediment bucket score, and also conducted several experiments in plume modeling in Central Water and Power Research Station. So here I have observed depth of score, width of score, length of score. As I earlier mentioned, plunge pool is the only solution to dissipate energy. So I have given geometry. Earlier researchers, they gave only score depth they have given, which is, am I audible?
Yes, sir. Yes, sir.
Yes. So which is not useful to any design. So in my research, I have considered length, depth, and location. Here only I have faced a problem. Lateral energy dissipation means width of score hole. That is only I have faced a problem. Okay, next slide, please. So I have compared with different schemes. This one. I also developed with weights and bias. I have proved some values. Later slides I will show you. I mean, parameterization analysis I have done with if you have any noisy data, how your output will be. So here, regression models I have used 25 for training purpose and 20 for validation purpose. I have considered discharge intensity, head, tile water depth, lip angle of the bucket radius as input, and so if it's the bed material. You can see this picture. Manish, you can play this clip also. This is the Parvati Dam spillway. Here you can see the score model with erodible bed material downstream side. Here you can see three spans. Here the discharge was 1850. This is 1:50 scale model, hydraulic model. Okay. Next slide, please. Next slide, please. Yes, you can see this upstream view power intake. So any power generation, if you maintain the full reservoir level, means power gamma QH, means you have to have full head, means full reservoir. So this is the left hand side. You can see before conducting experiments. This one after experiments. So for different discharge conditions, you can see exactly as per prototype we have developed the physical model studies. And the location you can see maximum how jet very far, almost in even model itself very far. You can see. And here what problem we face, the jet again going to hit in right bank side. So only option here you can suggest dam authority to change dam axis. So you cannot change to nature. So we have only option. So dam axis some tilt. Then you can see next photograph, next slide. You can see. Then yes, you can see water was hitting right bank. So bank treatment very difficult. Another hazard. So we have suggested dam authority to change dam axis. You can see the flow now at least okay, acceptable, not hitting. So here you can see two pairs, three spans in operation. Yeah, here simply I have conducted dimension analysis. Depth of score is a function of discharge intensity, head radius, bucket radius, lip angle of the bucket, tile water depth, bed material, gravity, specific gravity. Okay. Similarly, location of score and width of score. So by solving this using Buckingham theorem, I get this grouped variables. Another one previously raw variables. So these two I have taken as the inputs for even neural network models and also regression type equations I have developed. So you can see here relatively relative depth of score I have developed. See everything related to depth of tailwater. Correct? You should agree this one. Okay. So everything is. So here first one fall fraud number. So here statistical regression. These are my equations I have developed. This work published in 2005 in American Society of Civil Engineering, AC Hydraulic Engineering. Okay, you can see first parameter fraud number and also powers. So for any equations performance always how your error measures. That's what yeah, yes, these are the error measures. We always not depends on correlation coefficient. So the time I do remember Professor Julian, the editor, suggested root mean square we have to have some average errors and all, average absolute deviation. 4 error measures I have considered, and these are my results. Okay. Yes, you can see here the correlation coefficient still 0.84, and the only the error measures. Yes, you can see scatter plot. Sometimes scatter. Yes, it's still some scatter observed. You can see scala there sometimes under some over prediction and under predictions. So model you cannot generalize. Okay, that's why I have used the time neural network models. Okay, score depth you can see almost for low discharges, its model almost fail. I have clearly mentioned due to lateral energy dissipation. Lateral energy dissipation very difficult. I can see it's jet direction and okay, next slide please. Dr. Manish, next slide. So these are the typical examples. Okay. So why we need to have see plunge pool here. Now you can see that's why I again put same slides. Plunge pool location of score location where maximum from lip angle, lip of the bucket from main structure of the dam, and width of so the three parameters are very important to design and safety of dam. You can see here. So this much hazard happened for this much discharge, 1,50,000 cubic feet in one day, in 24 hours. This much happened. You can see right bank. So another case here, same problem in Srisalam Dam in Andhra Pradesh. So they are facing from year by year. So now maybe rainy season and floods. If all gates open, this is the problem. So here, I have also collected data from prototype data. See, you can see here in this picture, depth of score versus discharge intensity. This is highly scattered. See, there is no relationship. So I try to correlate, but nothing. Another head and score depth, highly scattered. So at time I used web propagation algorithm with the 2 inputs and 2 hidden nodes and 1 output. Here I don't get any data for width and location of score. This also 91 dams data I have collected from prototype observations, using several publications and also central water and power research station data. Okay. Here you can see 3 algorithms: feed forward propagation algorithm, feed forward cascade correlation algorithm, radial basis function, and ANFIS. ANFIS produced very good results. Still here you can see some over prediction and under prediction. So similar, using same data I used, and again I have published gene expression programming thing. I and Dr. Aitak went from Gaziantep University, Turkey. We have published several papers, he and me. You can also see high, very scarce, many outliers you can see here. Manish, Dr. Manish, previous slide, please. Previous slide, please. So you can see these are the 4 traditional researchers, Martins, Virenez, which Bureau of Indian Standards they are using, still using. So these are the formulas. Even USBR, small dams, and they both recommended. You can see highly means outliers and with the low correlation value. Okay. So again, I have developed similar like in the equation. This is my equation, which is this publication published in Journal of Hydraulic Research, 1.42 Q power. So you can see these are the comparison table. Yes. Yes. So here I want to show you first I using raw data. You can see left hand side 6 inputs: discharge intensity, head, bucket radius, bed material, and tile water depth and lip angle. So outputs are depth of score, location of score, and width of score. So this model works as a continuous model, which produced simultaneously, which I used MATLAB programming, developed feed forward, propagation, and radial basis function, and ANFIS. These are using raw variables, raw variables. Then another one you can see fraud number, then a relative head, relative bucket radius, and everything related to. So these grouped variables which produce very accurate. These are the so you can see network configurations, 6 inputs, 10 hidden nodes, and 3 outputs. And you can see RBF produced a fraction of seconds, means 2.5 seconds produced, but the results not that much. But always slow algorithm web propagation which produce good results, though it is slow. since this high networks always stuck up in global minima, okay, like LM, Livan. These are the comparison with model 1 and model 2 are the models. This work published in ASC Hydraulic Engineering. Yeah, so this model we recommended that time. So dimensionless input parameters, significant the inputs. That's what I want to show you. So we also done some sensitive analysis. If you remove one variable and how your output will vary. Yes, here you can see some sensitivity analysis I have done using raw variables. You can see the error how it varies. If all 6 variables, error will be reduced, and also correlation coefficient, very good correlation you will get. So in case of grouped variables, how it varies. Yeah, I also done. You can see same thing. I have with always we say non-limited black box models, but I play with the hidden nodes and the weights. Then I worked with this one, and I show you relative importance. You can see always ahead how much. Also fraud number. You can see exactly it's matching 56% weightage it gave. Also, yes, some parametric studies I have done changing variables like similar. That's why I have conducted 75 experiments. Means keeping one and changing different bucket radiuses, different bed materials. Actually, this was very laborious. But what to do? You can use flow many other models which don't give much accurate value compared to physical hydraulic modeling. So here also I done probability analysis. Means if you have any error, negative and positive, so how your output will be varying. So this one nothing but extraction of extraction of knowledge from trained model, which I published again in Japanese journal. No, you can see this one. This is what happening. How your output will vary if you have 10% noisy data or 10% positive or negative in the for model 1 and model 2. Yes, the range of hidden node approved means not black box. But these all designers are not comfortable during. So if you give any equations, and this is all another fuzzy logic. This will give many memberships rules, many members, but it gives very accurate results. And this, yes, these are the see. Here only problem is not like neural networks. We can use 3 continuous model. Here one output only at a time, each time. Yes. So one is raw model, another one is grouped variable. So these are the results, which gave very good results, but not work as a continuous model. So these are the conclusions. Some conclusions I have made. Still, what I want to conclude, whatever. So that is the main problem using hydraulic model. We are considering 2 mm, 3 mm, 4 mm D50 size. In prototype, actually, it gives only scoring pattern, which gives scoring pattern with using physical hydraulic modeling. In case of similar problem for bridge pier score, and I think Dr. Pandey done much work and abutment score. One of my student done for peer scores, with different angle of attacks, circular and square and different shapes for abutment and also peer score. Another student, my student done a score below pipeline, and also we also done for culvert score. So different hydraulic structures score around hydraulic structures. So here the still work is can be conducted using rock mass rating and rock quality designations as the inputs, but very difficult to get data as neural network needs much data. Yes. So another possibility still researching means model and prototype confirmations. So several 3 cases I have shown: Rana Pratap Sagar and Ukai Dam and Kariba Dam. So again, I have faced the lateral energy dissipation. So this weight matrix and all that, so designers are very quite unhappy. That's why I have developed. So I will share my papers, recent papers, gene expression program, which give accurate and designers will appreciate. So these are the. So here last conclusion, you can see increase in the lip angle. This is what the Sri Salem Dam they neglected. I don't know this common sense question. They implemented 30 degrees lip angle, or at least it should be 45 degrees. So something extracted trained model. So these are the again. In case of skid bucket, I have done, and for low flows also many other researchers have done for stilling basin, still scores, and many done for sluice gates also they have done. Yes, I have provided the time skid score package using MATLAB. So for future, anyone can use this rock quality designation and rock mass rating. So what my contribution again? I'm score geometry. The previous researchers only they provided a depth of score. So with that, we cannot design any flange pool.
The slides are finished. So due to the internet connection, I think we didn't get something in the, I think in the 5th or 6th slide, you explained one thing that
Okay. You can go back, please. Yeah, no problem, sir.
Dam failure. During the inauguration program, one dam was failure. So I think you may please.
Yeah, that one, Salal Dam spillway. Salal Dam spillway. I was explaining.
Okay. That was.
So, Salal Dam spillway. Yes, sir. This one.
Okay.
Dr.
So can you, sir?
Back.
Yes, sir.
One more back. Yes, this one Salal Dam spillway. You can see this much beautiful dam.
No, sir.
Go further.
This was.
Yeah, yes, sir. One more slide back. One more. One more. No, one more. Yes, wait. So this much beautiful dam, you can see the beauty of dam. I always show my students when I teach fluid mechanics. You can see white water, everything. So please observe here. Please observe. You can see white water, beautiful dam. So in front of you, what happened after 24 hours? Just one day, 150 cubic feet. Means divided by 32. Then you will get meter cubed per second. Okay. After inauguration, exactly happened whatever we want to know. So hazard example, this is the one of the classical example. Our Indian dam. Another one you can see Sri Salem Dam also same. Also another one Kariba Dam. Dam height 120 meter. The score means every 10 years you can see observe. I provided that graph. So it reached almost 2/3 height of the dam. So engineers mind breaking problem now.
Thank you so much, sir. Thank you
So
for
we must we must operate in full reservoir level. So you can see even freeboard also you can observe in Talal Dam spillway. So we need to get the power gamma QH. You have to have. I showed you in Parabati Dam spillway also upstream side power intake there. So we have to have. So we have to operate full reservoir level condition. So after several complications with Pakistan, this dam has completed. Okay, 1978. So here also many things they told we have to operate sluice. It means you need to sediment flushing everything. So we have several problems. Not only dams like Alameti Dam and state-wise. I worked in National Water Development Agency. That time also I do remember Andhra Pradesh was telling Alameti Dam height reduce, please reduce. We are losers. I was working several same problems, country to country and state to state in India. But this is another thing I must inform you. This is useful for Chandigarh state, Rajasthan state, and also Jammu Kashmir, and Punjab, and also Haryana. Many states for power generation. This one, and also Himachal Pradesh. All North Indian dams, especially NHPC. So otherwise, we don't have power, any power. Okay, Dr. Manish.
Yes, sir. Thank you, sir. Thank you. If anyone wants to interact with Professor Ajmatullah, sir, he or she can directly interact with him. Or I have also dropped his email ID. Anyone
Yes,
can
I,
write
now, Dr.
email to
Manish,
him.
what I will do, I have
Yes.
several other works. This one only I am showing here since beautiful dance related to India. So I'm talking. So several, I have done for peer score, and you also have done many things: abutment score and culvert score, score below pipeline. So here I must mention there is no much, see this much energy, you can see energy, there is no consideration of any climate change or anything. So high energy means heat energy generating. So there is no much means due to rock cuttings due to high velocity jets here. This was core mechanism is very complex, Dr. Manish, and previously late Professor Kotiari have done much work in peer score and bridge peer score, and Professor Subhash they also done. And you can also see Doliganga, another first slide. You can see model and prototype exactly happened. I do remember. I don't want to say here. That time, my boss Rajnikant Katsurya, which wrote a spillway book, he clearly mentioned upstream Doliganga something problem. He neglected that time. The director was one of the NHPC director. He say, when nature is going to do, why should I waste my money? So it happened. After 5 years only happened. I left CW Paris in 2006. Then after few years in 2009 and 2013, it happened. Exactly, I show you. This is another natural hazard. CW Paris has suggested that time. My boss was suggested. I was a research assistant under him. I do remember these words. Sometimes, our ego problems will create lot of huge damage.
Thank you, sir. Sir, please share this presentation with our participants. They will
Sure, sir.
ask
Sure,
you.
you can, yeah. And also, papers also. Sir, sorry for the internet. I'm really sorry. Here, heavy rains going on. This one small island, right?
Yes, sir. Due to
I'm
this
really sorry,
internet
Dr. Manish.
due to this internet issue, so we didn't get some informative introduction part of this slide. But we will try to read your presentation, and we will
Okay, sir.
try to
Thank you,
get
sir.
information about it. Thank you so
Thank
much,
you,
sir.
Dr. Manish.
Thank you so much, sir. If anyone have any
It
question,
was very
he or
good
she
internet
can ask.
when Professor Mahesh was talking. Then suddenly, when my time comes, it happened. I'm really sorry about that. Internet and
No issues, sir.
night for me and
Sometimes
good day for
things
you.
are not in our hands, sir. Thank you so much, sir. So
Thank
our
you.
next speaker is Professor P.V. Rao, sir, from NIT Warangal. So P.V. Rao, sir.
Yeah, I'm available.
Okay, sir. Now I'm making you the presenter. You may please share your slides. Sir, now you are the presenter. So this is the last lecture of today's session. So I just want to introduce P.V. Rao, sir. Dr. P.V. Rao, sir, currently working as Associate Professor in Department of Civil Engineering, and he is also holding administration post at NIT Warangal, like Associate Dean, Divisional Head of Water and Environmental Division. He has done BTech in Civil Engineering from Sri Venkateswara University, Tirupati in 1999, Masters in Environment Engineering from Anna University in 2002, and PhD from BITS Planning in 2011. His research interests and activities are water supply, treatment and distribution, wastewater treatment, waste management, low-cost water and wastewater treatment, anaerobic digestion of organic waste, waste of energy technologies. So Professor Rao sir authored more than 40 peer-reviewed journal papers and book chapters and presented 30 plus papers in national and international conferences. He has handled several research and consultancy projects, and Professor Rao sir has guided one PhD student and more than 30 master's students. At the present time, he is guiding 5 PhD students and 7 master's students. So now I request to Professor P.V. Rao sir, please start your lecture, sir. No, sir, you are not audible, sir. Sir, please unmute yourself, sir.
Am I audible now?
Yes, sir. Now you are audible, sir.
Okay, good. Okay, good afternoon to all. I would like to thank Dr. Manish Pandey for giving me this opportunity. I think my voice is clear?
Yes, sir.
Good. So I want to thank Dr. Manish for giving me this opportunity to talk on the topic river hazards in environmental perspective on a 3-day river dynamics, flood and sediment hazard assessment in Indian rivers. Indeed, I am also thrilled to get some literature in this area. Actually, my routine research area is wastewater treatment and water treatment, and also I work on solid waste management. So suddenly, when he asked me, then this is a area where I have done my master's thesis. So I recalled my experiences from master's thesis, and as well as all I consolidate all my experience of water bodies interaction with environment, and then I made this presentation. Hope this will be definitely useful to the participants. So I welcome you all for this river hazards, and as well as looking this river hazards from environmental perspective. Okay, so this particular image is a recently taken image which depicts the situation of flood in Maharashtra, state of Maharashtra, where you can see that the bus is completely submerged. That shows you about, as Professor Umesh has mentioned in the morning, about different zones of flood impact. You can now guess what should be the height of this inundation, and accordingly you can classify. This is a classical example of urban flooding. Now, coming to my talk, what I'll be talking today, my presentation will cover on first of all river hazards, like when this river hazards happens, how it happens, what are the characteristics of river supporting its different habitants, and when a river floods, how it floods, what are the different agents responsible for this floods, and what type of floods we can call them as flood hazards. And in such a case, if it is happening flood hazard, how do we communicate the danger of river hazard to the downstream people? And after flood, how do we manage or minimize the flood risk? During the flood, what type of impact will be there on the humans and other lives and materials in the environment? then what solutions we have in our hand to manage the flood, and all these points I'll not be talking completely technical, but rather I'll be discussing all the points from environmental engineering point of view. If you look at it as a environmental engineer, how do you look at all these things? So my perspective, I'll be detailing the discussion. Okay, and finally we'll have summary and discussion. So this is my presentation outline. So I'll start my presentation with one big statement generally we come across. The water resources structures, something like dams and embankments. This is what we call it as some structures which will protect us from sudden floods in rivers. Okay, so this is what the water resource engineers generally say, that these structures helps us to manage the water better, particularly during floods. We can store the water during dry period. We can use during non-monsoon. We can use this water for other purposes. So for that, they say that it is these dams and embankments are solutions. But if you critically look at it, can we call them as a solution, or is it the problem? Is it the structures themselves are problem? So that is what, if you look at it, these dams and embankments are the solutions of problems, particularly for floods in rivers. So to answer this question, I am presenting few case studies. The first one on the top, my left hand side, which you can see here, you see here, this is basically a case of floods in Uttarakhand. This Lord Shiva was completely washed away. Statue was washed away in that particular floods. Here you can see the encroachment of the river bed itself for this entertainment, like for for amusement purposes. They actually built these structures within the river course, main flood path. Then if we expect these structures are being washed away because of flood, it makes no sense. So we should have a basic common sense and as well as a civic approach when what to do, what type of constructions we can take along what type of stretches. Going further, these images will show us what type of devastation, how catastrophic it can be, a flood, what and all it can carry in the river course, what type of damage it can cause to the human habitations in case of any severe flood. You can see all sort of material being carried in the river course. So these examples will tell us what could be the quantity of water that is available in the river bed, which is entering into human habitation area to carry all these materials into the river course back. Now, to answer this particular question, as I told you in the beginning, the floods in the river, which are caused by dams and embankments. So the answer is, while the dams and embankments are often touted as interventions for better flood management, but they often have been found out at the root of more severe flood disasters. We have seen such scenario very recently in almost all the rivers passing through our two Telugu states. That is, the two major rivers are Krishna and Godavari. And the river Krishna, we have seen very recently, it has witnessed the flood not even starting of August. In the month of July itself, the river has seen the flood and lot of water has gone into the ocean. So to understand this particular phenomena, how these floods are happening and how these hazards are arising out of flood. So first let us try to understand a little bit more about river from environmental point of view. So if I want to define river, it's a mechanical, ecological and geotechnical system. And it seems to be very surprising and difficult to understand and digest, because you look at the part of river and river dynamics, then the definition or the things which I am talking about here, it gives you a justification. And the flood, what we are talking about, the flood, river flood or river hazard, I can term it to be a natural disaster. I can categorize it to be a major physical event generally occurring in the environment, causing severe impact over the biotic and abiotic factor. The biotic factors are the biotic factors which are getting impacted are living within the river and as well as on the adjoining areas. And abiotic factors, once again, there will be a change in the river. There may be a change in the river course. There may be a lot of inundation and changing its path on the adjoining areas, which may happen suddenly or over a period. That depends on how much flood it is happening, how much runoff it is carrying, and so on. So the damage, particularly what I was talking about, severe impact. So the damage arising out of the severe impact, that can be in terms of loss of life, material and environmental damage, which severely affect the economy of a country. And mostly the floods are seen or projected always as a detrimental impacts on the environment. There are positive impacts of floods on the environment as well. Today, if you look at the rivers, most of the rivers, they carry or they are receiving the wastewater generated from the majority of the cities. If you look at today the urban environment, there are several cities which have formed or which which have been urbanized. Example, the city Allahabad on the shores of river Ganges. The entire city's sewage, partially treated and partially untreated, finally getting left into the river Ganga, which we treat them as very sacred. Now, if these floods would not happen, imagine how many years would it take to self-clean its own riverbed and along with the water. So the floods definitely had some good impact on to maintain the water quality of the river itself. So if you look at it, the floods and its impact, there will be impact on ecosystems. So these ecosystems will undergo an unexpected modification. The unexpected modifications includes its change in number, evolution of new species, extinction of existing species, change of river course. These are some of the examples which may happen generally after the floods. So if I want to strictly analyze how flood happens, how flood takes place. So the flood is a body of water overflowing the river channels. The floods are associated with some extreme natural events that happen over a drainage basin. So this is a general terminology which is being used by our water resources engineers, I will be using this information from environmental point of view to elaborate at some places. So to make my perspective to be more clear, I am just using their terminology and some discussion to start a discussion from environmental point of view. So the drainage basin may comprise rural or urban populations. And whenever flood happens in rural areas, that happens mainly because of flooding of rivers only. But in case of urban areas, if it happens floods, there need not be floods from the rivers, but the urban area can be flooded just because of their poor drainage conditions. So whenever rural areas are getting flooded, it is just because of it. Most of the times it is because of the overflowing of water bodies. But in case of urban areas, need not be the reason of only overflowing of water bodies, but maybe because of several poor drainage conditions that are likely present in case of urban areas. So if I want to define the floods, they are defined as the relatively high flows which overtakes the natural channels provided for runoff. So whatever channel which is provided for runoff, if that channel can take care the runoff generated from the rainfall, so it won't inundate, it won't result in inundation. But otherwise, it is likely to cause the flood. So the level at which the water flows along the streams is called as river stage. So this elevation of water or the river stage is the one which is decided, and accordingly in our country, the concerned regulatory agencies, they will issue the warning stages. They say that level 1 warning, level 2 warning, level 3 warning, like that. So these warnings are issued just based on the river staging. And based on the river staging, as water resource engineers have been modeled the river basins, they will come up with, based on the river staging, they will tell how much area will be getting inundated, what could be the possible loss, what should be the proper evacuation strategy to minimize the loss of life and property through different channels. So during the flood, particularly flooding time, the stage of river is very, very high. So the river water during the flood usually overflows its banks. As long as the water flows within the banks, it is unlikely to inundate the adjoining areas. So here we'll be introducing one more term that is called as floodway, which is the channel of water course and those portions of adjoining floodplain which are reasonably required to carry and discharge the floodwaters. So from environmental point of view, the river offers a very good habitat to many living organisms. So there happen to be a lot of interactions between the biotic and abiotic components of this river, which determine the strength of these ecosystems. More diversified it is, instead of having a very specific populations, if you are able to analyze the river ecosystem, and if it is having several micro and macro species, we can say that that particular river ecosystem is enriched and it is a diversified system. And it is also to note that the river water is an excellent carrier of nutrients, and every life prefers staying near to it. Let it be not only humans, even the other living species also prefers to stay very close to rivers or within the river zone. So most of the time, the river stage is below the channel banks, maintaining the sanctity of the rivers. At the time of higher discharge, water overflowing the banks are likely to cause the flood. at bank full stage, the water fills the channel up to the top of the banks, and that is the channel capacity, beyond which if the water flows, then the river starts flooding. And the wider river channels are formed when there is enormous outflow of water over a flat region. So here, unlikely the banks are going to be there. The banks almost like a imaginary or a flat region. Over a period of time, the running water as a geological agent, it develops canyons, gorges, waterfalls, meanders, floodplains, and deltas. So what are these canyons and gorges and waterfalls, meanders? These are all different formations which naturally happens because of water as a geological agent, and I'll be showing the examples of all these things in my further discussion. And because of all these things, it forms something called floodplain of a river, which is clearly definable, the physical feature of its valley. So it is the flat area bordering the river. So let me show you water as a geological agent, what and all it forms. So first, let me show you canyons. So these canyons, which you can see here, so these are the natural geological formations which are formed because of water as a geological, because the water finds its way through this place. So over a period of time, water as a geological agent, it forms a clear path between this, these rock formations. So these type of formations are called as canyons. Not that every river or the floodway, it is formed by all these phenomena. So these phenomena are responsible for this creation of this water carriageway. The next thing is gorges. So these are the two extremes of gorges, which you can see here, one on the left and one on the right, which are formed. These are all natural, like nobody has created them. And these are waterfalls. And fortunately, all these, both the waterfalls which I shown here, are taken from the state where this institute is also established, so the state of Telangana in India. Next, these are all meanders, which you can see here, which are formed through the thick vegetation. Next, you have something called floodplains, and you have deltas after this. So these are the different formations water as a geological agent. Now, a floodplain is built up of layers of sediments deposited by the river when it periodically overflows the normal banks. And these floodplains are generally flat and near water are desirable places to live. People have long been attracted by the floodplains for settlements. And even farmers, they love to cultivate the floodplains because they are very fertile. And if you look at it, some of the rivers in our country, that is Brahmaputra and Ganges and Indus rivers, they are having the largest alluvial plain, and that becomes hotspots or the most preferred locations by these farmers, particularly for cultivation. And large and thickly populated cities, industries, capitals are located along the river courses. So that shows that how important the floodplains, how they are being used now at this point of time. And whenever flood happens, it is important to communicate to the affected people to minimize the loss or damage. So there are different modes of flood communication. So first we need to identify the locations. So how do we identify these locations? And as it was explained by professors preceding to me, there are several models available which can forecast for the given intensity of rainfall and drainage area, which areas are likely to be getting flooded, to what extent, what could be the inundation, possible inundation in that area. So based on this modeling and prediction, they'll come up with a warning system and identifying the critical areas which are likely to be getting flooded. So that is how we choose the identification of locations. So once we identify them, we can use various communication channels because the urban people are much more connected. So reaching them is much easier. Today, in this era of advanced communication systems, all the people are connected with internet through mobile devices and so on. It is extremely easy to convey the message to urban areas. But look at the areas which are susceptible for flooding, where the people are living in rural areas, isolated, decentralized, and you have to use effective channels to communicate to these people through mobile SMSs, even All India Radio and so on. And it is also important to communicate to these people, not only threatening them or creating a confusion. So there shall be a system on issuing a warning based on what is the threat associated with the monsoon forecast or prediction or rainfall. So to what extent the evacuation is important, what type of rehabilitation measures they're required for a given rainfall and intensity. So you have to make proper indications to understand the inundation and signposts, etc. And these marking levels and signposts shall not be something like random. So we need to have a scientific study to tell what type of warning we can issue based on the severity. Now, it is evident how good you plan, how well you design. You cannot be absolutely get away from floods. It is mandatory. It is a fact because floods are natural disaster events. You can't completely control them. We can't control nature. We are part of nature. But what we can do is we can minimize the losses that are likely to be associated with the floods. That can be human loss, other biotic, other living species, or abiotic materials, whatever it could be. We can only minimize the loss, but we cannot avert, we cannot stop, or you cannot divert the flood. It is not possible, literally not possible. But by doing effective planning, we can definitely ensure that the things which are exposed to floods can be minimized. Then how do we do it? So even though we know that the floods cannot be completely controlled, even though we have several strategies to manage the flood effectively, but what goes wrong generally? Why there is a lot of loss of life and impact on abiotic resources. Still having knowledge of all these things in this era of development, I have listed here something I call them as frequent reasons for increased vulnerability. The most important reason is increasing economic and developmental activities in floodplains. Then somebody can ask me the question, are we against the economic and developmental activities? No, not so. But where you have to undertake these activities, those identifying appropriate locations are much more important. Particularly in a democratic country like India, we are influenced by several agents, several factors. Basically, is the agents. I would use a term called factors. You have social factors, political factors. Because of these decisions, these circumstances, even though our engineers, water engineers, they predict the probability of flood in an area, even if they earmark or if they say that that particular zone is to be zone 3 or zone 4 as per Professor Umamahesh in the morning lecture, still the regulators are not listening to these predictions or good work done by water resource engineer, and finally we are ending up in taking up such economic and developmental activities in floodplains. So obviously it is not the mistake of nature, it is a mistake of human intervention who are undertaking this type of developmental works in the area where they are not supposed to be. And lack of regulations. So there are different regulators, there is a lot of miscommunication between them. By the time they give permission, some initiators would be executing the project already. I will give an example for this. In all the urban areas, particularly I take the example of the capital of the state of Telangana, Hyderabad city, there were several multi-storied buildings which were constructed in the water bodies. They encroached a lot of water carriage ways within the city. After encroachment, they will apply for regularization. So government charges penalty and regularize that construction. Then who will be suffering? Because of this irregular construction or illegal construction which was made by encroaching these natural water carriageways, they not only harm themselves, they're also responsible for loss of property and inconvenience to the neighborhood. And another reason is, even though it is required certain drainage system for an urban area, and because of several deficiencies, we end up in designing inadequate drainage system. This is not happening just because not having financial resources. There are so many angles out of it. Improper prediction of growth of the city, or the actual implementation of drainage system in an urban area from the design. There could be a lot of deviations. So all these things may result, and non-maintenance of all these drainage systems which are constructed may lead to more vulnerability of the flood in the urban areas. And next and last, I need not tell this, in our country, very recently, we are seeing that there is a disaster team very recently. Since my childhood, actually, I'm an environmental engineer for last 22 years, but I could see that the rescue team for particular disasters, I see that it is very popular only last decade. And we were not ready to spend money on this particular issue. We always take the case that, in case of flood, we say that only loss of property and life. Not only that, there are several important points which we need to consider, because in case of flood, if somebody is living person's health is getting damaged, it is very likely that it may happen that the health may be getting damaged because of the flood. And that should be seen from human point of view. From humanitarian grounds, you have to look at it. What is the loss of man hours? How much his hard-earned savings are spent to recover back to the original health? All this happens just because of improper preparedness for disaster. And now, having known what could be the impact or vulnerabilities, particularly for flood, then what strategies do we have in our hand to manage the flood? One thing is modify the flood. We cannot avert, but we can modify. What can we modify? We'll discuss further. And we can also modify the susceptibility to flood damage. As we know, as we understand from the predictions of water engineers, what can be getting affected, understand, and then plan to minimize the damage. Modify the loss burden. And ultimately, which you can't modify, you have to bear the loss. This is unavoidable. As much as we do it, beyond which things will not be in our control, so we have to take care of that. Now, here I'll be showing an example. So, different zonings in flood management. So, this is a normal channel through which the normal river course takes place. Here I showed you different colors. I showed you dark blue here. So this dark blue is a frequent flood. And here you can see that another color which is given here. This basically shows you flood once in 25 years. And you can see the flood once in 100 years. And now, if you take due diligence, if you take complete information about what is the level of inundation in the adjoining areas, and give permission for setting up of such establishments in the area, because as I told you, it is impossible to not to have a flood. It is very, very likely that every area is to be getting flooded. But how frequently? That depends on how good you design, how good you understand, how good you design your flood drainage, local drainage conditions, and how equipped you are. So accordingly, the permissions can be given here to manage the flood. If I want to show that as a elevation with reference to river cross section, so this area which I am showing here in the blue color is the prohibitive, and this restrictive zones where we can give only permission to very restricted amenities. By taking the level of inundation into consideration, we can design those structures, those amenities, those facilities. And these facilities where we can give permission, but with sufficient warnings, such that the losses that are likely to be arising can be minimized. Now, going further, If you look at it, urban environment, I focused more on urban environment because these urban environment are likely to be getting impacted very frequently. Even a very small rainfall also, they're getting flooded. They're getting flooded. It's one thing. The second thing is that is causing a lot of inconvenience to the people, majority of the people living in the urban areas. One of the major reasons for this urban floods, let it be flood in Delhi, flood in Hyderabad, flood in Chennai, flood in Bangalore, floods in Kerala, the reason is transformation of vegetated land into impermeable surface. Now one can ask the question, in the new urban environment, how can we have a vegetated land as an open without having an impermeable surface? Are we not for concrete structure? Are we not for pavements? The answer is not that somebody is against for impermeable surface, but you have to provide enough opportunities, avenues for the rainwater to enter into ground. Don't simply blindly seal, pack everything. This one activity of transformation of vegetated land into impermeable surface, leading to a substantial decrease in the proportion of rainfall, particularly runoff, that infiltrates into the ground. That is the natural way of, I would say, the natural sink of runoff into the ground, which will ensures the vanishing of the excess water flowing onto the ground. And this also leading to increase in the surface runoff because of this more impermeable surface. In addition to that, because of our more encroachment of urban drains, as I mentioned earlier, why people encroach urban drains? Because they are easily encroachable. These are not properly marked in the surveys, and there is enough corruption. There are enough, in the absence of any the strict regulatory, these things are happening. And another failure is the failure of drains to carry the excess flood water. And of course, I should not say that flooding of sewers. This happens if there are sewers. If I take the case of the capital of this state, the Hyderabad city, the most known city one of the most known city in the country, is still today, as on today, is having only 60% of city is only covered with sewers. The 40% of city still is not having sewer. And for this entire state of Telangana, the only city which has at least some known amount of or known area covered with sewer is only Hyderabad. The rest of cities in the entire state of Telangana either not having sewers or having sewers covered less than 10% of their territory. And in addition to that, they're also having enough poor maintenance of urban channels, no funds allocated, nobody bothers, thickly grown vegetations, illicit dumping of urban solid waste, and not to tell leaving industrial effluent into these urban channels, escalating the problem like anything. So, as I mentioned earlier, the main causes for this urban environment floods are mainly blockage of this urban and impermeability of this nature, And sometimes even to handle scenarios, this problem is going to the next level because of failure of drainage pumps. And sometimes just to save the people, the municipality also opens sewer manholes. That means they will open the sewers for taking the flood water that is runoff. And even if some planners, they have balancing storage, and either connecting will be a problem, or the approach channel for the balancing storage may not be properly maintained. So that also may be leading to failure of this balancing storage. Now, we talked about what are the causes of urban flood so far. Now, what happens if really flood happens in urban area? Who is the real sufferer? The first thing is we will not have the potable water. The municipality will not be able to give the potable water because the water treatment plant itself must have been submerged. Your underground wells are completely filled with flood water, direct contamination. You have sewers overflowing. So the sewage comes in direct contact with the urban runoff, and both are getting mixed, which will attract several waterborne diseases, and which also may lead to severe interruption to normal life in terms of electricity, transportation, essential food elements. There will be no milk supply, food supply, your proper communication system, network, everything will be getting affected. This is one side. The other side, what happens is when it comes to rivers and lakes and rural areas, you will have non-point source pollutants enter into the rivers. The agricultural fields, which are farmers they are using now in the modern agricultural era, they're using a lot of pesticides and nutrients. There is no scientific study still in India which regulates the use of the pesticides and nutrients. There were so many awareness created to the farmer, but still farmers are not following majority of the guidelines given by the respective regulator in order to use how much nutrients, what stage, pesticides, and so on. So all these things excess are finally coming back to water courses. Coming to urban environment, people started habituated for several products into their day-to-day life, right from floor cleaning to cosmetics and different types of products they use in urban life. All these resulting as a emerging contaminants in the urban runoff, which are arising out of flood. All these things we have to show the final path, destination. Now, in order to handle such a bad situation, like as we discussed that, it is impossible to completely avoid the flood. I communicate them. I understand that the problem, what are likely it may cause because of flood. Now, what do I have in my hand to manage the situation? I could do something called sustainable urban drainage system. What is this sustainable urban drainage system? I am talking about only urban areas. I am not talking about rural areas because of the time given to me. Here, what I proposed here are the possible strategies. One strategy is diverting runoff from impermeable surfaces to soakways. So don't seal everything. Keep enough open areas. Keep proper vegetation. Keep rainwater harvesting pits in the every area. Design them properly. Execute that. These rainwater harvesting pits not only to avoid from the floods, these will help us recharge your groundwater. So the very next day, whatever you are using for our day-to-day purposes, you are anyhow going to use some of the groundwater. So to replenish the groundwater, use the soak pit. So and allocate enough budget, enough money to do so. And if it is already made the surface to be impermeable, then make the surfaces to be permeable. Make enough provisions. Don't always think to carry the water to next place. Any place today, a city center or maybe abutting area may be underdeveloped. After a few years, that area may be developed. So if you try to take the water from that area to very next area, once again that area will be getting flooded. That becomes a core part of city. Sometime later, once again you have to handle that area. So rather, don't think of a solution just taking the headache from my head and put on somebody's head. So try to solve the problem at the same place where it is being originated, and creating temporary storage for runoff, like have balancing reservoirs, ponds, underground storage tanks. These are something called in situ solutions for small buildings. And then incorporating swales like shallow sloping drainage ways that have the attributes of storage, local conveyance, and infiltration. So these are some of the few initiatives which we can term as a sustainable urban drainage systems. Now, I want to do something called engineered solutions. Okay, it's okay, small scale, okay. Now, from engineering point of view, what I can do. So, as I mentioned a few minutes back, it is impossible to completely avoid the flood, but we can minimize the damage that are likely to be associated with the flood. So what I can do is I can come up with something called defenses. So the defenses, we can do proper design and modeling, and by considering the uncertainties involved, risk involved, and the environmental consequences, I can come up with an appropriate defense. So what is this defense? Now, if you look at it, this is a normal catchment under given scenario. This is expected to flow like this. This is a normal scenario. Whenever flood happens, the rainfall, you can say the intensity will be very high. It gives you more runoff. When it is having more runoff, that it crosses the banks, and this area, you can see that the adjoining area also will be getting inundated. This is a normal scenario in case of flood. Then how do we handle this? Through engineered solution. Now I have drawn this picture once again. Here in my next slide, you can see this is a flood scenario. This flood scenario, I can overcome this flood scenario by having a elevated bank. If I have more elevated bank, then what I can do, I can match my inflow with the flood. I can also release the same outflow. I cannot store the flood water. By raising the flood, an embankment here on both the sides, I will accommodate the same outflow to leave my place through my river course to my floodplain. Thereby, I am protecting my neighboring areas on both the sides. So this is one solution. So if I want to summarize here all the solutions, so I will be having options something like, there could be several options, but I consider or categorize them into these heads. Thing is, I do something called some temporary storage. When I have something flood, just take that excess water and put it in some place where it will not cause any trouble to me. Or whatever headache I am getting, flood excess water, just leave it to downstream. Let the downstream fellow see that all the problems. Or I do something like, I know that something is going to happen, so I design accordingly. I take care I make enough provisions in my building such that even though the water inundation happens, nothing happens to their life will not be getting affected. You design accordingly. There are engineering solutions available. When it comes to temporary storage, we can take the water and store on a farmland. See, in our country, all times, all the fields may not be cultivated throughout the year. So identify enough land where, because all these are not applicable everywhere, wherever possible, there are different options. Next, I can have a regulated flood storage reservoirs. I can do the river restoration, like by removing the sediments. In case of leaving the water to downstreams, I can have raised defenses. I can also use diversion channels, not to trouble my downstream area, but take the water to the place where there could be shortage in the downstream. And if you look at it, both the states, Telangana, Andhra Pradesh, there are enough areas in the state which doesn't receive enough rainfall. So the backwaters that are obtained from these major dams of Krishna and Godavari, people are using that water to take to some other areas which are water starved. So this is an example of raised defense in a normal scenario. In case of inflow, how this likely to be community A and B are getting inundated in case of natural condition. And by having the raised embankments or properly planning defenses, I can see the community A here is protected from inundation. The same thing with community B also. Now, having discussed about the various options, so what is the road ahead, particularly for the flood risk management? One thing is have good flood awareness. I don't mean only to the public. I say that this flood awareness should be created among the regulators, among the people who plan the public facilities. Listen to the water resources engineers, what they tell. Their predictions should be honored. We should move from the book to implementation. And don't only give importance to the loss of life and property. Think of the suffering of a human and other life because of the inconvenience caused due to floods. You have to be humane and have appropriate planning. Do the designs for flood mitigation measures. Of course, you need to be looking after asset management, how to protect the assets. For that, you need to provide enough funding, you need to have enough resources to safeguard the things. So with these strategies, if you follow, we can minimize the loss that is likely to be happening because of the floods. So this is a photograph taken from the city where I live. This particular place is very close to our institute, just 1.5 to 2 kilometers from an institute, the place where I live. You can see that area, how badly it is inundated. So thank you all. So this is from my side. Now the floor is open for discussion.
Thank you so much, sir, for the informative lecture and presentation. Now, if anyone wants to interact with Professor Rao, sir, he or she can directly unmute his or her mic and ask their queries. So I think there is no query, sir. Thank you so much, sir. So here we are closing our today's session. So tomorrow we have 3 more lectures. First lecture will be delivered by Dr. Manish Goel, sir, from IIT Indore. Second lecture will be delivered by myself. And third lecture will be delivered by NIDM site. So mainly research scholars will present their research work on disaster related issues. So here we are closing our today's session. So tomorrow we have 3 more lectures, and please make sure participants for issuing e-certificate from NIDM side, you have at least 80% attendance. So only 3 lectures are left. So please make sure about it. Thank you, Rao sir. Thank you, Uma Mahesh sir. And
Thank you, Manish.
thank you, Fatima ma'am. And thank you, Anil sir. And thank you all the participants. So here we are closing our today's session. Tomorrow we will meet at 10 a.m. Fatima, shall I close?
Yeah, sure, sir.
Okay. Thank you so much, ma'am. So we will meet tomorrow.